Thank you for your invitation to visit. I really very much appreciate it, and your very kind introduction. Actually, the pitch Stephen Fahey gave to me for going to Berkeley was, come here, it's a great town, there's great physics, and umbrellas work, the rain falls straight down, because of course in Ireland there's so much wind coming in off the Atlantic that you can't use an umbrella. But anyway, yeah, so like many of us, a lot of good scientists have helped us along our way. And in particular, I want to reinforce what Lena said, that I have since '84, since I started at Berkeley, I've never done science alone. I actually think it's the reason why I'm a good scientist, because we all bring a certain outlook, and you can do better science together, particularly in my area of science, which is laser science, where we need to understand the applications to understand what light science we need to do. And so these are just some of the graduate students and postdocs who contributed to this. It's started making short X-ray pulses for my PhD thesis, and it took a few decades later to where we had control over coherence in the X-ray region. So it's a very long journey, but enjoyable. And of course, the science is, the science, of course, is always done by people. And so in the 3 talks, I'll be talking about 2 groups of people. First is the KM group at JILA, run by Henry and myself out there at the back. And then, of course, they're always very happy when they graduate. And then in the 3rd talk, I'll talk about the Strobe Science and Technology Center, where essentially what we're trying to do is invent we call it, our tagline, the microscopes of the future, the microscopes that don't currently exist now, where you could take a functional system and watch motions from the electron and atomic scale in a thick sample. That microscope doesn't exist right now, but we have another 9 years to try to do it and combine that with computational imaging. So I'll talk about that on Thursday. Okay, so this worked, of course, a minute or 2 ago, and some reason is not working now. Let me try to do one thing. Okay, good. Okay, so in my talk today, I'd like to tell you how our community learned to have, I could argue, and it's fine if you don't agree, but I could argue that we actually have better control over light in the X-ray region right now than we do in the visible region. It's fine if you don't agree. This is a little bit for fun. But essentially, quantum physics is allowing us to sculpt a radiating electron wave function, do that on a cycle-by-cycle basis. So we're now able to have complete spectral, temporal polarization and coherent control in the X-ray region, not using optics, but using the driving lasers, where we have great visible driving lasers, where we have wonderful optics. And I would never, as an old plasma physicist who used to make X-rays essentially with a sledgehammer, just you take a laser, make a very hot light bulb, where we had no control. The X-rays went everywhere. You absolutely no control. This is something we just would never have anticipated. And of course, it was a whole bunch of grad students and postdocs working together, literally tripping over things and figuring out that actually we can do this. So we have now we're not as powerful as the free electron lasers or synchrotron sources, but we have better control over the synchronization, the waveform, and the coherence. So it's a very complementary light source where we can see things they can't see, and they can see things we can't see. So it's very nice. And then, okay, you'd like that to be useful. And so in my talk tomorrow, what I'd like to tell you about is why this capability is really useful for understanding correlations in materials. I can make a quick energy argument, exchange splitting, electronic energy levels, they are all associated with very fast dynamics. If you have coherence, you can get you can make very short pulses, and with X-rays you have an ability to probe. You have elemental, chemical, and spin contrast. So you have an amazing tool with which to probe interactions in materials. And the interesting thing is that we've seen that some traditional spectroscopies that we've been using for quite a while are actually blind to many excited state dynamics. They just can't see the excitation. So I'll explain how we see what's going on and what are the new types of spectroscopies that can take advantage of this light source and that we can use to discover new things about materials, and also new regimes of nanoscale transport. And then on my talk on Thursday, I'll talk about what coherence gives us in terms of imaging. Just briefly, until now, because we had no good X-ray optics, we couldn't make a good X-ray microscope. And your typical X-ray microscope was about 10 times diffraction limited. You just could not make a good image. But now, because we have coherence, we can now implement sub-wavelength imaging in the X-ray region and are developing these functional microscopes. Okay, so we've had coherence in the visible for, it's shocking because I've been around for as long, but Mayman did, demonstrated the visible laser in the red region of the spectrum back in 1960. And I don't know if any of you would like to guess what the shortest wavelength laser that's in widespread use is. Anyone want to guess? 97? Excuse me? 97, okay. And if I ask then for manufacturing, anyone guess what that might be? It's photolithography, exactly. It's 193 nanometers, the excimer laser. So you think about it, in almost every other area of technology, you've had, if you look at data storage or computing power, you've had many, many orders of magnitude increase in capability, but in lasers, we've had less than a factor of 4. And that's one of the reasons why these quantum harmonic sources, they're interesting, because it turns out they're currently the only way to make a coherent short wavelength beam on a tabletop, apart from the beautiful free electron lasers. It's the only other way. And why would that matter? Well, if you look at a lot of our correlated materials, superconductivity, transport. We're just talking with Lena about her energy class, photovoltaics, a lot of those things. And as we try to optimize them, understand first of all what's going on, and then try to do iterative design, we're looking at things that have length scales on order of nanometers, and time scales. If you talk about spins and charges, those time scales are on order of sub-femtosecond on up. Now, X-rays have always been fabulous because they can penetrate your body if the energy is high enough. So they penetrate materials, a big advantage over visible light. They also have characteristic absorption edges, and the position of those edges change depending on what the material is, what its chemical or oxidation state, and also its magnetic state. So you've got inherent contrast. You don't have to add any fluorophores or such. However, if you don't have coherence, then you can't take advantage of the next 2 points. Because if you don't have a decent lens and you try to make a microscope with a bad lens, your microscope is only as good as your lens. And so even though the wavelengths are matched to nanoscale objects, you don't have a microscope that can access that. And even though your frequencies are super high, so at a keV, a single cycle of light is 2.5 attoseconds. But that doesn't do you any good if you don't have coherence, because you can't add the waves together to make a short pulse. So this is why we would like to make coherent X-rays. you could make amazing microscopes that could look at a functional nanosystem in 3D, but you absolutely need coherence to do that. And so, and it's for this reason we don't have coherence, and that's why when you go to your doctor or your dentist's office, essentially they're using the same technology that Röntgen used to make the picture of his wife's hand. And when your poor technician is looking at your x-ray, you know, it's really not a whole lot better than that first x-ray. And the technology is the same. It's a more powerful version, but it's exactly the same technology. Essentially, you're making a picture with an x-ray light bulb. And this is one of the reasons why, you know, the resolution in x-rays are still nowhere near as good as it needs to be to actually detect disease better. Okay, so why was it so hard to make x-ray lasers? So think about if you want to make a laser, you need to put many, many atoms in an excited state. But the lifetime for an atom in a highly excited state, which is what you would need to do to make an X-ray laser, is very, very short. And in fact, it scales as the wavelength, the ratio of the spontaneous to simulated emission goes as the frequency cubed, and then you can do a back-of-the-envelope calculation on the power you need to power a laser, and it goes as the wavelength to the inverse fifth power. That may not sound too bad, you know, when you just look at the equation, but if you pop in some numbers, I can hold you know, a visible laser in my hand and powered by batteries, but if you go to 1 nanometer, it takes a terawatt of power. That's about the electrical generating capacity of the United States. So you are never going to have an X-ray laser, you know, working continually. Just is not going to happen. And by the time you get to an angstrom, you would need a petawatt of power. And it's for that reason that the first X-ray lasers were observed during nuclear weapons testing. And actually, there's a nice historical observation that for those of us who remember the Star Wars era, I was a grad student at the time, and there was a proposal to, you know, shoot down missiles by detonating nuclear weapons in space. Turns out the quantum technology I'm talking about came out of Star Wars funding. It was just interesting. And also, the first coherent X-ray source was not based on population inversion, but rather on electron acceleration. So this was the LCLS, free electron laser light source at Stanford. It's got a 2-kilometer long electron accelerator. This is the freeway interchange near Stanford. And this came online 50 years after the visible laser. And many of us, we were, I know I met Dan and others, we were in DC celebrating the 50th anniversary of the laser. And Steve Chu was the Secretary of Energy at the time. And we all know Steve has a great sense of humor. So Steve's quip was, it's an amazing, you know, device. It makes a millijoule of X-rays, you know, that can, you know, destroy anything and probe many, many materials. But it certainly wasn't free, and I should know it because I think with the LCLS upgrade, I think it's going to be approaching $2 billion. So the capability is fantastic for science, but not something that in its current form can impact, you know, other areas of, you know, broadly impact, you know, a lot of science or medicine or manufacturing. So it's very worthwhile to explore what of this capability can we reproduce in a tabletop setup. And so we use a very old idea. It's actually very interesting to look at the history of nonlinear optics. So the first time somebody took, in this case Peter Franken, took the ruby laser and changed its color. It was only 1 year after the ruby laser was demonstrated. Franken focused it into a quartz crystal, used a prism to separate the second harmonic light from the fundamental, and the young folks in the audience might not know that, of course, they didn't know how to do this very efficiently. So when they submitted the picture of the photographic plate for publication in Physical Review Letters, the typesetter thought it was a speck of dust and whited it out. So there's no experimental evidence, and you can check on your iPhone. There is absolutely no experimental evidence of second harmonic generation in this first paper, and they never submitted an erratum. Because anybody with a ruby laser, you could focus it onto anything, you'd get surface second harmonic generation, you'd see blue light everywhere. So everybody believed it, never published the erratum. So what was going on, and how can we use it, to get to the X-ray region? So what was going on is, your driving laser light is sinusoidal, but if you drive electrons in an anisotropic material, the electron trajectory need not be sinusoidal. If it follows an anharmonic motion, then you will get harmonics of the fundamental field radiated. And this is essentially what this 347 nanometer was. It was the second harmonic of the fundamental 694 nanometer light. So how far should you be able to push this? So clearly it's related to the anharmonicity of the motion, but you do have fundamental limits. In a material, you have damage threshold, and in an atom, you also need to be able to keep a nonlinearity. It won't work to drive the electron in free space. You need an anharmonic potential. So for that reason, for the next 30 years, the highest harmonic you could get was maybe up to the 9th, if you were lucky, and it was a much diminishing returns. There's a nice analogy with sound. If you think about plucking a guitar string or a violin string, and if you pluck gently, you would get the fundamental tone. If you pluck really hard, you'll hear harmonics. And then if you pluck really, really hard, the string will break. Yeah. But it turns out if it's an atom, that doesn't matter. And so it turns out that the best thing to pluck an electron in an atom, if you really are just interested in driving that system anharmonically, is a femtosecond laser. And as just that technology underwent a revolution in the 1990s, where we moved from dye lasers, which were very hard to control, just because they changed. The laser was a different laser every day. Didn't store a lot of energy. But fortunately, Peter Moulton, down the street at Lincoln Labs, had developed Ti-Sapphire material for NASA for space flights. And it turns out it's still the broadest gain bandwidth of any material developed, so, which is amazing for a laser to last that long, to be at the cutting edge. Normally, we were in a mode where every 10 years the technology would completely change. But Peter developed this material. It's got this huge emission cross-section that can support a 3 femtosecond pulse. And as luck would have it, the physics of this laser is such that it gets more stable if you make the pulse shorter. In every other laser we used to have, if you made the pulse shorter, the laser was harder to use. But the physics here, because it's based on a nonlinearity, the laser gets more stable. So you have this great laser. And just around that same time, between when Sibit demonstrated that you could make this material into a pulse laser, and our community figured out how to make very, very, very short pulses, just about that time, in 1987, Charlie Rhodes in Chicago was funded by Star Wars to look at harmonics in gases, and he wasn't using Ti-Sapphire. He used krypton fluoride, I believe, laser at 248 nanometers, but they knew something was up when they saw harmonics up to the 17th order, and that was 10 more than anybody had seen. Charlie tells the story that his funding agency said it can't be anything useful, so stop doing it, and so he didn't pursue it much. But fortunately, other folks like Steve Harris at Stanford, who had a nice Ti-Sapphire laser, did pursue it, and then very soon afterwards, like in 93, observed up to the 100th harmonic order. And by then, people knew this was not traditional non-new optics. How are they emitted? And this was, Charlie was advised to ignore since there was likely nothing new. But of course, now we know very well, what was going on. It's a fundamental response of all atoms and molecules to a femtosecond laser pulse. That so essentially, you don't need much energy, even less than a millijoule. But if you pack that into 10 femtoseconds and calculate the electric field, that is higher than the Coulomb field that binds the electron to an atom or molecule. So on the leading edge of the laser pulse, you will depress that Coulomb barrier, and then you have beautiful quantum tunneling. So every half cycle of the laser, your electron wave function can undergo partial tunneling and then move away under the applied laser field. But of course, that laser field is oscillating. So when the field reverses, it can re-encounter the atom or the parent ion. And then, of course, this periodicity in time, and convert the kinetic energy of motion into an X-ray. And the periodicity in time, if you do a Fourier transform, you'll also get periodicity in frequency or energy, and that's the order of the high harmonics. And now this has been observed out to the 5,000th order. Now this I'm explaining this as if the electron were a point particle. Of course, we know it's not. And this is a more realistic physicist. It's a simulation by Carlos Hernandez Garcia. You can think about this as the electron in hydrogen. And this is what's happening to the wave function as the hydrogen is being irradiated by an intense femtosecond laser field. You see the quantum tunneling? And because the quantum phase of the electron in the continuum is different from the part that did not ionize, you get you acquire a different quantum phase, so you get quantum interferences then that leads to a very beautiful spatially modulated wave function. And think about it, so this is a fundamental frequency, but the fact that you have spatial modulations makes it look as if you're accelerating the electron at much higher frequency. And that is the actual microscopic origin of these high harmonics. So this is this idea that if you write down the dipole moment, what we're trying to do is calculate the second derivative of the dipole moment, the acceleration, so we can use Jackson and calculate the radiated field. So you've got a three-step process. You've got tunnel ionization into the continuum, propagation in the field, and then recombination back to the ground state. The propagation in the field, that quantum phase is proportional to the laser intensity. So that means that the quantum phase acquires many radians as the electron is in the continuum, and that's what gives rise then to the quantum modulations on the wave packet. I have another little simulation here just to sort of give you a feel for the physical origin. So there's too many graphs on this, but you see the Coulomb potential, and this is a 1D representation of the electron, 1s state in hydrogen, and our laser peak is going to be here. So now you can see we're beginning to, so let me just stop it for a moment. You can see the wave function is spread over many Bohr radii. We're nowhere near the peak of a 20 femtosecond pulse, but we've started to ionize, this is that wave packet, we've started to ionize the atom. And now let me continue a little simulation. And you can see just about now that the ionization of the atom has happened over this 5 femtosecond interval. It's during that 5 femtosecond interval that you have a dipole. The modulations give rise to small oscillations on the fundamental dipole, which will give us the radiated high harmonics. But you can see that that you only have a nonlinear dipole for a very small time. If I let the simulation run out now, So you can only get radiation while the atom is ionizing. So the femtosecond laser is plucking that electron wave function in hydrogen, but it takes about, since it takes 5 to 10 femtoseconds to ionize, during that 5 to 10 femtoseconds you can emit these really high order harmonics. So essentially that's why the laser field can be quite long, but your emitted X-rays are always much shorter, only while the atom is ionizing. And there's a nice analogy with the X-ray tube that think about if you were going to take Röntgen's X-ray tube and say, well, can I redesign this to be quantum coherent? Then you would want your ionization step to come from some quantum coherent state, and that's the ground state of the atom. You'd want your electric field to be coherent, and that's the femtosecond laser. And you'd want your target to be coherent with the initial state, and that's when the electron is recombining with the part of the wave function that did not ionize. So every step is quantum coherent. And everything I just told you we've known for 25 years. We couldn't make the nice simulations 25 years ago, but we knew all the quantum, well, Ken Kuhlander, Ken Schaefer, others knew all the quantum mechanics of strong field tunneling and light emission. And from any one atom, it's a dipole transition, so you have a dipole radiated field, no beam. Very, very weak dipole emission. And what took our community a long time to figure out is how could you phase match? Now remember, they had figured out, Blumbergen had figured out this about 2 years after the laser was demonstrated. But we had our community had a much harder time seeing, well, how could we take the emission from many atoms, make sure the electrons were recombining at the right time so that the X-ray fields would add coherently. And it looks like an easy problem. And part of it was that you sort of needed to mix together atomic physics, strong field physics, laser science, and nonlinear optics, and nobody knew all of those fields. And we weren't even going to the same conferences for the first 10 years, so everybody was talking past each other. Because the concepts are not that hard, but it just took a while to realize. Now, you might say, well, how hard could that be? So your laser comes in, interacts with an atom and emits an X-ray. If you want a phase match, you want the laser field and the X-ray field to both propagate with the same phase velocity in the medium, and if that happens, you will get coherent addition. But you know, in a prism, blue light and red light do not travel at the same speed. And in a plasma, that's also true. In fact, for X-rays, nothing bends them. So for the most part, the X-rays are traveling with the phase velocity given by the speed of light in vacuum. But the laser light is slowed down in a gas and speeds up in a plasma. Okay, so thank you for the, okay, so I can use that. So essentially you can, this is again our theorist collaborator, Carlos Hernandez Garcia, to try to convey how hard it would be if nature hadn't figured out how to do it, is you can think about your laser field as being a quantum conductor trying to get the same number of atoms as there are people on Earth to sing in tune together. Moreover, it's worse than that because I don't have the right scaling on the fields here, because the laser light can be 4 micron, but the X-ray light is 1 nanometers. And if you want things to add up coherently, you better get that addition to at least the 10th of the wavelength. So that means you've got to line up to less than an angstrom spatially. And at that same wavelength, your cycle time is 2.5 attoseconds. So you have to line up to also a fraction of an attosecond. And there is no electronics that will let us do that. It just can't be done. So you have to figure out the physics. And we're very fortunate that nature does it passively if you set up the right conditions, because we would have no hope of actually doing it actively. So how does it work? So this is one slide on how it works. That this is the laser field as it interacts with the gas, and it starts to ionize. Remember, that was when we saw the quantum tunneling. Now, the ionization is shown in green. Now, the ionization goes down here. That's when the electron wave packet recombines. And so the ionization will reduce, and that's when the X-rays would be emitted. Here, the X-rays are going with a phase velocity given by the speed of light c, but the laser is traveling in a gas, so it's going too slow. In a plasma, the laser phase velocity speeds up. The group velocity doesn't, so it's fine. But that means that somewhere in between, the laser light will also be traveling at a phase velocity given by c, and that window depends on the color of the driving laser. So it's really cute because we actually have a Pockle cell that we just control by the driving laser color, and we can arrange for the X-rays to be emitted during one half cycle or multiple half cycles. That gives you periodicity or non-periodicity. It gives you a comb or a coherent supercontinuum. And so it's very nice that we have that capability. And so we have a little recipe here that sort of doesn't show the quantum physics, but it shows the recipe that works, that if you want short wavelength light in the vacuum ultraviolet or extreme ultraviolet or soft X-ray region, this is the driving laser wavelength you should use for the simplest form. There's other fancy ways that you can use and that get around this, but this is the most straightforward way of making high harmonics. So if you want KeV high harmonics, then you need to use these 4-micron mid-infrared driving lasers. And it works. We shine different color lasers into a gas-filled waveguide, and then we get out X-ray beams in different regions of the spectrum. The most remarkable one is work we did with Andrus Baltuska's group in Vienna using a 4-micron laser in a 40 atmosphere pressure gas. This is sort of interesting because it phase matches over a 12-octave coherent supercontinuum, and this is very interesting from a chemical or materials perspective or magnetics perspective, because this coherent supercontinuum spans many absorption edges, and this is just showing you how we can sort of change the spectrum from being periodic in time and frequency to an isolated burst in time and an X-ray supercontinuum. And that's a really nice capability to have. I don't know if any of you have worked at synchrotrons, but X-ray optics are very lossy if they even exist, because we don't have a good wave plate, for example, in the X-ray region, and we can do all of that with light. And we don't know where the limits of this light science are, because if you really wanted to answer that question of where are the limits, can we go to hard X-ray, for example, you would have to combine 3D time-dependent Schrodinger equation to figure out the quantum, that wave packet spreading that I showed in the movies, and then combine with Maxwell, and that gets harder and harder as your driving laser is getting longer and longer in wavelength, and your emitted X-rays are getting shorter and shorter in wavelength, and there is no computer fast enough to do that calculation right now. So that's why we don't know. Our back-of-the-envelope estimates with our theory collaborators say should at least be able to get to 15 keV, because there's another issue, as we all know, for example, Lorentz drift, that if you pull your electron away and if it's in the continuum for a long time, it will tend to drift. And so the question is, how do you make it recollide? People have ideas. You can make counter-propagating lasers and such. So, but that's another reason why nobody knows the limit, because nobody can do the full theory calculation. So it makes it an interesting area. Just telling you a few of the surprises along the way, that for decades people thought there was no way to control the polarization. And that's because that's the movie I showed you. If you use a circularly polarized laser, you ionize the atom just fine, but with circular polarization, the electron never returns. If the electron doesn't return to the parent ion, there's no recombination, recollision step, so there's no emitted light. Now, it turns out that the theorist, Wilhelm Becker's group, had figured out this 20 years ago, but none of the experimentalists read the paper. There was about 2 sites, and then we discovered it with Oren Cohen's group, and we also figured out how to phase match. So we did do something, but Wilhelm was so happy because he said, geez, why did you never, realize how to do this? And we just, at the time, it really was an atomic physics question, and we didn't realize, but if we wanted to look at magnetic materials or chiral molecules, we would like to have circularly polarized light. So it was a good example of how people were just in different places, so it took a while to get the idea out. So what was Wilhelm's idea? Is use 2 driving lasers that had opposite circular polarization, and then this is what happens. You ionize the atom, but the electron actually recombines. So it's hard to tell from that movie what the radiated field would be, but you can do it in the photon picture a lot easier. So in the photon picture, you're making your high harmonic photon from the combination of red and blue photons. So you just conserve energy, as always. But you also have to conserve photon spin angular momentum. And the high harmonic photon can only carry 1 unit. It either has to be left or right circularly polarized. So you can only grab 1 more or less red or blue photon. And then whatever you have more of, then your high harmonic photon keeps that polarization. So it's really gorgeous. The circular polarization imposes another selection rule, and you get these sort of crazy spectra where now you get pairs of harmonics where the one is left and the other is right circularly polarized light. And you could not make this from any optic, and we can actually, that's what it looks fairly simple in the spectral domain, but this is what it actually looks like in the field, what the light field looks like. So this is theory, and you can actually measure this. It's not easy, but you can do it, because this is a 1 femtosecond interval. So we think it's one of the most complex coherent light fields today, because you're changing the direction and frequency of the light field on a really, attosecond domain. And it actually, we can actually confine that now to actually 1 burst. That's quite interesting if you want to understand some spin dynamics in materials. And so, and we can actually play tricks if you actually cross use 2 driving laser beams instead of being collinear. Now you cross them, then you actually can control the direction of the harmonics. So this is like having a spectrometer made out of visible light. So it's very interesting, the actual amount of control we have in the X-ray region now. We're manipulating the radiating electron wave function, and it is giving us this amazing capability to control the temporal coherence, the spatial coherence, the spectrum, the polarization, and in a way that none of us would have predicted. A lot of this has happened over the past 10 years or so, and we would have been happy to have a useful linearly polarized laser beam, and now it's just even better that we can get better control. So this is why I say we sort of have a tabletop complementary capability to the beautiful free electron lasers and synchrotron sources. They're very complementary. Of course, the large-scale facilities are much brighter, but we have better synchronization, the ability to go well below a femtosecond to look at charge dynamics. And the thing that's my favorite is, the next 2 lectures I'll be talking about some applications, particularly in quantum materials. And we were able to find out new things about the materials. And I say it's not because we're particularly smart, but we had the light source in our lab. So a student could look at some results and say, oh, they don't quite make sense. Let's do this test. So if you can test rapidly, of course, you can often experimentally determine what the mechanisms must be. And so I think it's the fact that a student can make the discovery because we all know they're smarter than we are anyway. And so it just gives, you don't have to write a proposal, you can really make a discovery in your lab. And so that's why we say that we're really in a time now where it's going beyond demonstrations, because in every single material we looked at, whether it was a magnetic material or looking at thermal transport in nanoscale structures, looking at dope materials, looking at quantum materials, charge density wave materials, fast switching materials, every one of these materials we learned something new that we did not anticipate learning when we went in. We often went in with one idea that this is what the material was going to do. The data would tell us otherwise, and then we had to, work with the mechanical engineers or the NIST magnetic group or our folks who grow us our different quantum materials. So let me just give you, for 5 minutes then, just give you a small intro on what I'll be talking about in the next 2 talks. Just to make the point that, our field of ultrafast phenomena, as we went from, and some of us actually saw this happening from picosecond to femtosecond to attosecond, you have to think differently how you make the measurement, because if you look at the uncertainty principle, if you have a 10 femtosecond pulse, and we write the uncertainty principle in terms of its energy time, and then if you put in 10 femtosecond here, you get 100 millielectron volts. You can still distinguish a different band or a different orbital in a molecule or a different band in a material. However, once you go to attosecond, if you've got a few attosecond bursts, then you've got tens of eV of bandwidth. So you will lose the ability, if you just continue making the pulse shorter, you have to figure out a different spectroscopy. And that is possible. And we now know we don't exactly skirt the uncertainty principle, but what you have to realize is these harmonic sources are a little bit like squeezed light. You don't get a Gaussian envelope. You get attosecond bursts every half cycle. And so we're able to make a high energy and a high time resolution measurement. We do sacrifice something, and I'll tell you what we sacrifice, but we can still make the measurement. We know how to sculpt the waveform to make either a sub-femtosecond measurement or a femtosecond and longer measurement. This took a while. And what I'll tell you tomorrow is how the other interesting thing we fell over was that normal spectroscopies, like magneto-optic spectroscopies, photoemission spectroscopies, they can't actually see excited states of material. Because if you highly excite, for example, a magnetic material, you will have a very highly excited spin state, but that it hasn't dissipated into magnons that cover the whole band, and you just can't see it with a regular spectroscopy. And so all of the onset of light-induced demagnetization people were measuring was just how energy was coupling from high-energy magnons to lower energy magnons. It makes sense. We just didn't know it wasn't this other exotic spin flip scattering mechanisms. And the other interesting thing about these strongly correlated materials is that we now know how to watch what the charge does when you excite it and see if it preferentially couples to different phonon modes. So this is another it was not anticipated. The idea when you would use a femtosecond laser to excite a material, the old story, which I learned in grad school and we used to understand, was you coupled light to the electrons because they can absorb very quickly, and then those electrons interacted with the phonon bath, and the phonon bath would all warm up on approximately the same time scale. We now know that does not happen. If you've got strong electron-phonon interaction, your excitation will couple to certain phonon modes, and that coupling can last, that hot phonon distribution can last a really long time, like 100 picoseconds. On the time scale of phonons, this is quite long. And then the other thing I'll try and tell you about is, so how would you look at these? This is a femtosecond, 100 attoseconds, 10 attoseconds, 1 attosecond, 100 zeptosecond. first of all, are there interesting things going on in materials? And yes, there are. It's, momentum redistribution, charge screening, scattering, and how would we, look at this what sort of spectroscopy can we use to look at these processes? And we've at least taken the first steps in showing that you can do it. And then, and in case you're not able to come to tomorrow's talk, I won't even bother telling you what we're measuring here. I'll just ask you to look at this vertical axis. So this is some quantity. It's electron screening and scattering that's going from 1 attosecond to a femtosecond to a picosecond. So we can actually make these measurements now. That's in time. In space, this is showing we've driven down the resolution of X-ray microscopes to the sub-wavelength regime. And the interesting thing is it's faster than the best microscopes eyes can build, which is kind of shocking, because who would have thought a quantum technology would do that? Okay, so our field, we've come a long way from where we used to be using sledgehammers to make X-rays we burned through this about maybe 10 years ago. I'm sure the senior folks in the audience, know this, but this was, it's like any technology, all the technologies that come out of Harvard and MIT, it starts off being very painful to those graduate students working in it, because, it's just, even to just get the light is a painful thing. But over time, on our, in our area of science, we've sort of just burned through this now. One of the reasons is we finally brought engineering, and this I need to disclose, of course, this is a company that Henry started, but I just wanted to show you that at least it's beginning to look like a laser. It's a reasonable size and reasonable stability. And so that means we can actually use it now for applications. And the fiber laser technology, this is just a comment. Fiber lasers have been around for 30 years, and fast fiber lasers, but it's only now that they're getting to the right parameter space that we can use them for high harmonic generation, which means that we can actually make the setup smaller, so they're more practical for use by other scientists. This is just showing that, this is just comparing with NMR. We're not saying high harmonics will be as important as NMR, but this is mainly for the grad students that often, the fundamental science, and we'd love to be able to make this a case, of course, to Congress, but it's hard, but it often does take 50 years from when you learn something new about nature to where it becomes a widespread technology. And it's interesting to see this with we saw it with femtosecond lasers, and now of course they're used LASIK and other machining, manufacturing, and there's a good opportunity with high harmonics because of this microscope technology that you can't make a diffraction limited X-ray microscope unless you have coherence. We'll talk about that on Thursday. So I hope I've given you some feeling for why high harmonic generation is an interesting quantum technology. We don't know where the limits are, but it is allowing us to make interesting measurements on materials. And I need to end with acknowledging the collaborators, and in particular Carlos and Luis, who made the beautiful simulations, and the quantum conductor, our theorists, strong field theorists at JILA, Andreas and Agnieszka Becker, collaborators, Chip Durfee, Oren Cohen, who worked on the circularly polarized harmonics, and Andrus Baltuska, who's one of the best laser builders in the world. And with that, I'd like to thank you for your attention.